Welcome, everyone. It is a pleasure to see so many people here. Old faces, known faces, not old, sorry, known faces, and not yet known faces. And I'm happy to meet a lot of new people this week. And so we're going to start right away. And sorry, I had the title here, but I lost it now. With Josephine. Josephine from Georgia Institute of Technology, and she talks on polyhedral combinatorics of polynomial ideals.
All right, thank you, Lisa. And yeah, thanks for the organizers. Well, having us here together, allow me to speak here. So I'm giving one of the introductory talks. So I hope that my goal is to make this accessible to everyone. So if you have any questions, interrupt me at any time. And also, I'll try to make it not technical. That means that there'll be some times where I'll be hiding some technical details. Yeah, I mean, you're welcome to ask them about it. I may tell you, or I might ask you to maybe, wait until the afternoon session. Okay. Yeah. So, let me see. All right. So the title that I gave was Polyhedral Combinatorics of Polynomial Ideals. So suppose you have some ideal in a polynomial ring, right? In some polynomial ring, and for today's talk, we'll assume that the ground field is algebraically closed. And then the main question that I want people to keep in mind is because I'm focusing on combinatorics. So the main question is, what can we say about combinatorial properties? What can we say about combinatorial or discrete properties? Right? What can we say about discrete properties of the ideals? Or of the variety defined by the ideal. So the variety is living in, right, k to the n, defined by the vanish n. So variety is all the points in k to the n such that all the polynomials are 0. What can we say about this set in algebraic geometry using combinatorial properties or polyhedral combinatorial properties of the polynomials using properties of the polynomials. So what do I mean by combinatorial properties? Anyone has some idea? So if I have some kind of polynomial, right? What are some kind of nice combinatorial information that you think we could extract from it? Maybe. Let's see what you think. Anybody? Maybe my question is not very clear. Yeah. For example, maybe, right, if you have a polynomial in one variable, right, I don't know, 2x cubed minus x, right, plus 1, something like that, right? It could be maybe the degree of the polynomial, that's what I mean, right? Or it may be the set of support, right? Maybe like I own, like right here, x cubed is there, but x squared is not there, right? X is there. So all the monomial support, right? These are the kind of thing that I'm thinking about, okay? So now let me first focus on how about what do I mean by the combinatorial properties or discrete properties of the variety, right? So it could be discrete, something like the dimension of the variety, the degree of the variety, right? And let me do a special case. Let's do a special case. 1k is equal to n, so I have the same number of polynomials as variables, right? And then let's suppose that for even simplicity, let's say that coefficients of the polynomials are generic. So that means there is nothing special, right? There's no sort of coincidences among the among the coefficients, we're going to expect, n polynomials and n variables are going to have finitely many solutions, right? Yeah. Oh, I'm sorry. Why? How can I? Okay, thanks for the, yeah. K for my field. You know what? Okay, I'm going to keep this K and then it could be big K. Very good. Yeah. Okay, great. Thank you. Okay, right. So in this case, the variety is finite. Then we can ask, what is the number of points? Right? So, well, finite. Then this depends on where we're counting. So in a projective space, in projective space, or in that case, we're going to need. It's not just this, but let's say we sort of you homogenize and go to the next dimension. You put stuff at infinity, right? I'll just write it, right? Okay, I'll just write in words in projective space. This is given by the Bézout theorem. Right? We know that the number of points, if counted with multiplicity, if counted correctly, is equal to the product of the degrees. So this is Bézout. Yeah, so that's right. In this case, yeah, if you have same number of variables, same number of equations as variable, and coefficients are generic, right? Yeah, zero dimensional if it is finite. Okay. Also, actually, a little more subtle. There is nothing too weird about the support. For example, although these are like n variables, but if they're secretly like, if like say like x1 is never used, right? Then in that case, it's going to be 0. Okay, right? So there are some weird stuff that can happen, but avoiding weird case, right? This is the Bézout theorem. Okay, so modulo some weird cases. So now, how about we don't do projective space? So I'm going to introduce another. So this was I wrote down the reference. Bézout is from many years ago. Right. So this is 1779. 2 variable case, 1 back to Newton's in 1687. So, but in 1975, there is another theorem called Bernstein theorem, or Bernstein called Minkowski theorem. So Minkowski is here in Toronto. So this is about, instead of projective space, we're looking at the number of solutions in the algebraic torus. So in A star to the n. Right, so this is an interesting case for like applications. For example, if you're looking at solving system of polynomial equations, and then if the variables have some kind of physical meaning, then you might want to exclude zeros because they're kind of degenerate cases, so maybe physically not meaningful, right? So in that case, they said that. So this is a very useful case. So the number of points in your variety, number of solutions for your system is equal to mixed volume of Newton polytopes. So I will explain to you what that means. Okay. So this is MV for mixed volume. And by new, I mean Newton polytope. So I will demonstrate this in an example. Oops. So suppose I have 2 polynomials and 2 variables. So let's say I have my f1 is 2x plus 3y minus 5xy. That's my first polynomial. Then I have second polynomial, 1 minus x, 7xy squared, something like that. So coefficients are generic. And to get to the Newton polytope, so this is related to what I was talking about, like it's like a monomial support. Newton polytope is the convex hull of the monomial support. So for the first one, I'm going to take, this is 2 times x to the, you ignore the coefficients because the count, if the coefficients are sufficiently generic, the count is not going to depend on the coefficients, right? So for most choices of coefficients, you get the same answer. So you ignore the coefficients. And then this is x to the 1, y to the 0, right? And then this y is x to the 0, y to the 1. And then xy is x to the 1, y to the 1. And then you take the smallest convex set containing those, that is called the Newton polytope. And then you do the same for the second one. So yeah, there is a origin somewhere, but then if you think about it, you know, if I can just translate the polygon, it doesn't matter because translating this polygon right here corresponds to multiplying this with a monomial, right? And if I'm counting number of solutions without zeros, right, multiplying or dividing monomial doesn't change this, doesn't change the count, right? So I don't really care about monomial. I don't care about translation of the polygons, right? So, and now I do the same thing for the second one. So this is 1 is x to the 0, y to the 0. X, this is x to the 1, y to the 0. And x to the 1, y to the 2. Okay, so I have these 2 Newton polygons. Okay, to get the mixed volume, so in the 2 variable case, mixed volume, here is one definition. Mixed volume of 2 polygons is equal to area of the Minkowski sum. So you just take a point, a blue point and a red point, and you just add them. You get another polygon minus area of the first one minus area of the second one. Then you can imagine something inclusion exclusion formula works for any number of dimensions. Yeah, you have a question? Yes. So this is P1 plus P2 is, I'll say, this is A plus B, such that A is in P1, B is in P2. Yeah, thanks for the question. Yeah, so this is called the Minkowski sum. I'll draw a picture. So another way to think about this is, you know, I keep one of them as my anchor, and then I look at, like, say, I keep my blue one. And then I take my red, I pick up my red polygon. Imagine it is like a wet sponge, right? And then I take the wet sponge and I just like trace all the blue point around, right? And then let's see which part of the blackboard got wet, right? So that is my Minkowski sum. So I could draw like this. So I could start with this blue one. And then if I put my wet sponge right here, right? So I get like this. And if I slide it to the right, along the blue line, right? And then I have my red right here. And then I will slide it down along the blue line. Okay, so this is the Minkowski sum for this example, Minkowski sum of these 2 polygons. And then if you look at this area of the sum, this whole thing, minus blue area minus the red area. That means that in this picture, you can visually see the mixed volume as the sum of the areas of these 2 parallelograms. Right? So another way to say this is this is the area of mixed cells, total areas of the mixed cells. Any other questions? Got my water bottle somewhere. No problem, no problem. Okay, so I hope this theorem convinced you that Newton polytope is a nice combinatorial, right, information that you can attach to a polynomial, right? So then it is natural to ask, what is the Newton polytope of an ideal. Right? So we talked about Newton polytope of a polynomial, right? What is a Newton polytope of an ideal? So I'll just give away the answer. So I'm trying to convince you that the answer is what is called a tropical variety. So let me first define tropical variety of a single polynomial, and then we'll generalize to the ideal. So here's a definition. Okay, tropical variety of a single polynomial is equal to the union over all the edges. So you take a union over all the edges, say edge E of the Newton polytope, and then you sum is a normal cone or normal vectors. So let me demonstrate this in this example up there. So I think I'll just try it again. All right. So in this little example, I have if you have this is the Newton polytope of my polynomial f1, right? And then you look at all three edges, and then in this case, you just look at the normal vectors. Normal cones are just rays, right? Normal cones are the cone of all the normal vectors to the edge. All the normal vector, what I mean is like another way to think about it is that like it's just the linear direction, where if I try to maximize the linear function in that direction, I should get the edge. Right? This is another way to define the normal cone. But like geometrically, yeah, think of just the normal vectors, right? And then so the tropical variety is a union of these three rays. Yeah, here I'm choosing the outward pointing normal vectors. You can also choose the inward pointing normal vector. You get an isomorphic theory. So I'm just making an arbitrary choice. Right? And then for the other red polygon, right? So I get let's see. Get this ray in direction -2, 1, right? And then this ray and this ray. Okay. And I can also remember how long the edges are right here. Here, all these edges have lattice length 1, right? You say that, well, okay, this edge has length square root 2, but then if I normalize it to the lattice, right? So between closest lattice points, I'm going to renormalize it to length 1. Then everything here has length 1. Okay. So right here, this has length 1. Although this looks long, right? There are no lattice points along this edge. So that means it has length 1. So pointing to the right has length 2, and going down has length 1. Yeah. So these are the tropical variety. And then, so I'll remark that going from Newton polytope to tropical variety, I haven't actually lost any information. If I know this, maybe I should draw a couple more pictures. Maybe that might be a little better. So if I look at the Newton polytope of, let's say, for example, 1 plus x plus y plus z, right? You get the standard simplex in 3 dimensions, right? So you have 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1. You get the simplex in 3 dimensions. And then to get to the normal vectors, you can first draw the normal vector to the facet, to the triangles. So normal vectors to the triangles are going to be minus, is it minus E1? No, maybe this is minus E2. Yeah, maybe this is minus E2, minus E1, right, minus E3. These are the normal vectors to the, right, the 3 triangle at the corner of my orthant. And then I have the normal vector to this big triangle up here. So this is going to be it's kind of hard to draw, coming out of the board in the direction E1 plus E2 plus E3. And then every 2 triangles meet along an edge. So that means that to get the normal cone to the edge, I just connect those normal vectors to the normal vectors, right, and make them a cone. It's kind of hard to visualize, but it is just, 4 rays in 3D, and then any 2 of them span a cone. So this is the tropical variety. Maybe another example is if I take 1 plus x times 1 minus 1 plus y and 1 plus z. Does anybody know what the Newton polytope is? A cube, right? A 0, 1 cube. You can think about expanding it, right? If you expand it, you get all the monomials, right? Well, the exponents are all the 0, 1 vectors, right? So Newton polytope is a cube. And here I should mention that, if you take the product of polynomials, right, the exponents add, you get Minkowski sum of the Newton polytopes, right? So Newton polytopes work well with the products. Okay, so Minkowski sum of 3 line segments is a cube. The cube, then, yeah, does anybody see what the tropical hypersurface might look like? If you look at all the normal to the edges, or if you look at the normal vectors to the little squares, and then you connect them accordingly, what kind of things do you get? Yeah, Lisa?
Like the three.
Yeah, the three.
Yeah.
So the 3 coordinate hyperplanes. Yeah, you get 3 coordinate hyperplanes. Okay, so the okay, sorry, my drawing isn't that great. Yeah. Okay, so 3 coordinate hyperplanes. All right. So these are tropical hypersurfaces or tropical varieties of a single polynomials, right? So these are polyhedral objects. What was I going to say? Oh yeah, and I will remark that the Newton polytope can be recovered uniquely up to translation from the tropical hypersurface. So right here, right, what I know about, if I see the tropical hypersurface, for example, right, the vertices right here, how can you see the vertices of the Newton polytope from the tropical hypersurface? Like, how do I figure out how many vertices are there if I know this picture? If I don't show you this picture, but if I just show you this picture, how would you recover the vertices? Does anyone see? Yeah, if you specify length for this race, right, they tell you sort of how long the edges are, right? Okay, and then so that if you look at this one, this vertex, right, correspond to this cone right here, which is not in the tropical variety, right? So this vertex right here, I'm sorry, wait a second. I drew this very badly, no? Okay, I'm sorry. No? Yeah. Okay. I drew this. So hold on. Okay. Yeah. Okay. Yeah, that's better. Okay. Sorry if that was confusing to people. That was I was using the wrong convention, right? So right here, this vertex right here, right, will correspond to this region that is not in the tropical hypersurface, right? And then this vertex right here will correspond to this region, right? This vertex will correspond to this region. So vertices are in bijection with the connected component in the complement of the tropical hypersurface, right? And then you can see if two vertices are connected by an edge, if these regions are separated by a wall, right? And then the direction of this wall tells you the direction of the dual edge, right? And then if I remember how long the edges are, right? So then I know everything about my polytope up to translation. Okay, so it just looks like, I just make my life more difficult. I just go from this nice Newton polytope to just this more complicated thing. But a nice thing that you can do with these tropical hypersurfaces that you cannot do with the Newton polytope is that you can treat them like a variety, like geometric object that you can intersect them. Okay, so this is the advantage of working with the tropical hypersurfaces. So here's the definition. So for an ideal I, right, so ideal I in some polynomial ring, so you can define the tropical variety as you intersect over all the polynomials in your ideal, the tropical hypersurface of your ideal. Right? So it is very much like in the classical case, the algebraic variety is that you take all the polynomials in your ideals, you look at the vanishing set and you intersect them. In classical case, you don't need all the polynomials though, you can just take the generators, right? So here in the tropical world, things are a little trickier. It may or may not be sufficient to take the generator, right? So I will remark that it may not be enough to use only the generators, use only generators of I. Well, it is known that you can do with finitely many. You don't actually need infinitely many, although I wrote like an infinite intersection, but it is not clear which finitely many you need. So the finitely many you need is called a tropical basis. And I believe that there is no good algorithms to compute it. One will hope that it's something like Grobner basis that you can just compute them, but right now we don't know. So it's like a computational challenge to compute a tropical basis. Okay. Any more questions? Yeah. Yes. Then the tropical variety would like potentially smaller than it gets, but at this like unit vector along with the like horizontal axis. Oh yeah, okay, that's a great question. So right here, if I just take, yeah, thank you. Thanks for the comment. So right here, if I just take the ideal generated by F1 and F2, right? I will want to, so if I take ideal generated by F1 and F2, so according to the definition, I'm going to have to intersect this one and the second one, which is this. So the intersection is just this ray, right? But it may not be enough. I may have to put in more things. For example, let's see if we can do this in real time. I didn't prepare it. If I somehow maybe eliminate, this x and this x, right? So if I take 2 times the red one and add it to the blue one, I get this one is gone, right? So I get 2 times 2 plus 14xy squared plus 3y minus 5xy, I think. Okay, this is also in my ideal. And then let's see what is Newton polytope looks like. So 0, 0, 1 xy squared. I'm sorry. This is 1, 2. This is 0, 1. Right. Oh, okay, no, this is still not helpful yet. Okay, so yeah. I was trying to find a polynomial that witness. In fact, if you throw in more and more polynomials, even this ray is going to be gone. So the tropical variety is just going to be a single point at the origin. Okay. How do I know that? Yeah, that's a great question because there's a theorem. Yeah, so there's a theorem that says that the dimension of the tropical variety is the same as the dimension of the original variety. And the original variety is 0 dimensional, therefore my tropical variety is going to be 0 dimensional. But then you can be like, okay, why can't be like 1,000 points along this ray, right? There is also another, well, in this case, I also know that these tropical variety is also a fan. So that means that if a fan means that if there is a point in the tropical variety, that the entire ray is in the tropical variety. And also, yeah, let me write down these ones. I was going to anyway. Okay. So maybe if you're bored, yeah, you could try to find some more polynomials that will cut out this this segment right there. Right. So some nice properties of the tropical variety. So. One is that, yeah, I'll just say that tropical variety has the same dimension as I mentioned. So dimension, maybe I should first start with the fact that tropical variety is always a polyhedral set. It's a polyhedral fan. So it means that it is more precisely support of a polyhedral fan. So if you are familiar with polyhedral geometry, you can take a set and you can give a different polyhedral structure, right? I could take like, this object and you can say it's a square, but as a set, it can just be also, right, this complex, right? Maybe they have different polyhedral structure. So I don't want to get into discussion about polyhedral structure. Let me look at it as a set. Right, as a set, it is a polyhedral fan, means that it is what I mean is it's a support of a polyhedral fan. Just a set is a union of polyhedral cones. And dimension of the tropical variety is equal to dimension of the algebraic variety, or which is our Kroll dimension of the ideal. Or ideal is quotient ring. I don't know what the, okay, but yeah. And then also tropical variety satisfies balancing condition. So balancing condition, you can visually see this as if you look at these rays, right? And if you look at the sort of the shortest lattice vector in each of these rays and you add them up, you get 0, right? So if you look at 3 blue rays and you add up E1, E2, and minus E1 minus E2, right? So this is very easy. Basically, you just take those rays and you rotate it 90 degrees. You get the edges in your polygon. All I'm saying is if you go around the polygon, you get back to where you started. Yeah, Mike.
So when you intersect two of these,
yeah. Great question, Mike. So Mike is saying, what if you intersect two of these things, right? Do you take? No. So when you intersect two of these things, first of all, they may intersect poorly, like in this case. Yeah. So they don't intersect transversely. So that's what we call not intersect transversely. If they are, if I just move the red one a little bit off to the side, right? Actually, I should. So in the tropical geometry, one way to resolve this situation of things not intersecting properly or not intersecting transversely is you keep one of them, and then you sort of perturb it a little bit. You shift the other one in a generic direction, right? So for example, you might get something like this. Okay, now they intersect transversely. And then right here, let me note that this picture is dual to this picture. Yeah, so it's not a coincidence. Right, and then you could sort of take right here, you take a generic vector, and then you sort of take the limit of this vector goes to 0, and then you can go back to the origin. That is one way to kind of deal with it. But okay, so what Mike's question is, what do you do with the multiplicities? So you don't take the minimum actually. So right here, the blue one will have come with blue multiplicity, and red one will come with red multiplicity. And then the multiplicity of the intersection is the product times, there is another multiplicity is coming from the direction of the edges. So it's, in this case, turns out to be actually basically the area of the dual cell. But in general, it's some kind of a lattice computation, like integer lattice. So you have an integer lattice coming from the blue cone, integer lattice coming from the red cone. You look at the integer lattice of the sum of the lattices somehow, right? And then you have to look at the index of the lattice in the bigger one. So there's some combinatorial lattice computation happening when you intersect things transversely. Yeah, okay, yeah, great question. So actually, this reminds me that I want to write things about the intersection. In general, right, if you take tropical variety, if you sum the ideal, in the classical world, you just intersect a variety, right? In the tropical world, you don't get you don't necessarily get the intersection of tropical variety, right? Life would be so much easier if these were equal, but in general, they're not equal. This is just inclusion. And then what I was saying about the perturbation, we do say that if I and j are generic with respect to each other, okay, so this is the case when I and j are somehow generic with respect to each other. I can make it more precise later if you want. Then this is equal to what we call the stable intersection of the tropical variety. Stable intersection is what you get by you fix one of them, you perturb the other one, you intersect, and then you take the limit back. So we have that. And then how about the other one, the tropical variety of the intersection? So this one actually works out well. This is the union of tropical hypersurfaces. So this is good news. So if you want to understand some tropical variety, you can look at its irreducible component separately. And also another nice property is that tropicalization is tropical variety is connected through codimension 1, connected through codimension 1 if I is irreducible, meaning the variety is irreducible, or is radical is prime, for example. Right. So let's see. And then I'll mention a word about Grobner connection. So right here, another way to define tropical variety, maybe going back to this, normal cones to the edges, right? So let me look at these examples. So for the blue one, if I take the blue one is F1 over here, right? So if I take the initial idea of F1 with respect to the vector 1, 0, for example, that means that X has degree 1 and Y has degree 0, right? So the initial idea of F1 with respect to 1, 0 is 2X minus 5X1. Okay, this corresponds to, in the picture, you can kind of see that if you take a vector pointing to the right, the points that maximize the linear functions are these 2 points, maximize these 2 points. As opposed to, say, if I take direction 1, 1, so X and Y both have degree 1. So that means that in that case, the linear function is uniquely maximized at this point, 1, 1, so which correspond to monomial xy, right? So I can rewrite the definition of the tropical variety as this is the set of all the wave vectors such that, the initial form is not a monomial. And then putting this together, I could say tropical ideal is all the weight vectors such that the initial ideal does not contain a monomial. All the weight vectors such that so this shows that the tropical variety is a subfan of the Grobner fan. Grobner fan is the partition or classification of all the weight vectors according to the initial ideals, right? So I'm looking at the initial ideals are monomial free. Okay. This may be a little bad news for those of you who like monomial ideals, because if you start with monomial ideals, of course, all the initial ideals are going to contain monomials. So tropical variety is empty. Okay. So if your idealism contains a monomial, your tropical variety is empty. Another family that people like is binomial ideal, right? So if your variety is generated by binomials, think about it. If you start with a binomial, what does its tropical hypersurface look like? What do you think? If you have a single binomial, right? Newton polytope is a line segment, right? So then, normal vector to that line segment is the entire plane. Yeah. So then if your tropicalization of a binomial idea is a usual linear space, you'll be intersecting a bunch of those usual planes, so you get a usual linear space, right? So those are sort of like very, very simple case when it comes to tropicalization. Okay, so I don't have that much time, so maybe I'll mention things that I have looked at where, nice interaction between commutative algebra and tropical varieties. So you can use tropical geometry or tropical varieties in computational algebra. So for example, maybe, so using tropical geometry in commutative algebra. So one thing you can do is to give dimension bounds. So because of the theorem, this is the dimension of the tropical variety is the same as the dimension of the variety, right? And also combined with the statement that, if you take, so for example, you have some large ideal, right? So there are some applications where, for example, I know some people have worked on these problems in n-body problem, where in celestial mechanics, where you have these, sun and moon and star and maybe some other celestial body. And then there is a big conjecture that there are finally many central configurations. Central configurations are the one where you have these configuration and you let go, everything just shrinks down to just a single point, right? So sort of like centrally using this Newton's law, right? So there are only finally many. Well, what it comes down to is showing that some huge system of polynomial equation is zero dimensional, right? So in theory, you could try to do it in Macaulay too or something. But then these are so huge that no computer system can do it. But what you can use is you can use this theorem that tropical ideal lives inside the intersection, right, of these tropical hypersurfaces. So there's some big system of polynomial system, and then this right hand side is some kind of a combinatorial, like polyhedral linear algebra computation, very big, but piecewise linear computation. And also combined with the fact that my tropical variety has to be balanced. So that means that the dimension of my tropical variety is upper bounded by like the smallest dimension of a balanced fan, right? Because we only care about balanced stuff inside the right-hand side, okay? Even if the right-hand side is very big dimensional, for example, if the right-hand side is like positive ortho, okay? If it is positive ortho, the only balanced thing that you can fit inside positive ortho is a single point, okay? So you have this, and if you can show that, this right-hand side cannot contain any balanced thing except a single point, you're done. You will have shown that the left-hand side is zero dimensional, right? So you can give dimension bounds using tropical variety. Right. And also you can use it to compute Newton polytopes of unknown hypersurfaces. Say, I know Claudia is going to be talking about elimination theory in the afternoon, right? So in elimination theory, you are in the, so in the case of polynomial ideals, right? So you have some ideal and some polynomial ring correspond to some variety. And then you take a coordinate projection. Let's say you project out the last coordinates, right? And then so you project out, right? Project out the last coordinate. So in the algebra side, you take the intersection of a subring, which is the thing that you're interested in computing, right? So let's call this J, right? And you get Vj, okay? So we can bring in the tropical methods to this picture. So you can tropicalize this thing. You can look at tropical variety. So depending on, this may be very difficult itself, but depending on the context, right? So maybe there's some combinatorial context or the case one, you have generic coefficients or things like that. There may be some situation where this is actually pretty easy to compute, right? And then coordinate projections commute with tropicalization. So you can go ahead and project the tropical picture as well, and you will get tropicalization of your variety. Okay. So then in some case, so this tells you something about your unknown idea right here, right? So right here, the problem is that you're given I and you want to compute J, which may be a difficult computation, but you can go toward the tropical variety, you project your tropical variety, you get some polyhedral thing. And then if this happens to be a hypersurface, right? If J happens to be a hypersurface, then this will tell you the Newton polytope of the generator, right? So from here, you can get information about J, for example, right? So this is one example of how tropical geometry can help with some problems in commutative algebra. So you can do similar things for like implicitization problems or resultants and discriminants and things like that. All right. So maybe I also, in the remaining few minutes, I want to talk about another project that I was involved in. Is some. Oh, am I? Okay. Okay, I thought, yeah, I should stop at 50, but maybe, okay. All right, then maybe I'm not in a rush. That's great. Then I can say a few more things. Yeah. Okay, now then, maybe instead of one thing, I'll give you a little more information. Okay, so yeah, in the remaining 13 minutes, maybe 12 now, I will talk about some commutative algebra problem motivated by tropical geometry. So some commutative algebra problems motivated by geometry. So, or even, well, okay, let's see. All right. So this is actually not even by tropical geometry. This is a purely combinatorial problem about polytopes, and I'll tell you. So suppose I have k polytopes in n dimension, and say they are rational polytopes. Maybe we can drop the word rational. I don't know. Okay. And then we could look at the tropical hypersurfaces. Okay, I haven't defined this, but these are just union of the normal cones like before, right? Before I define, tropical variety of a polynomial, right, to be the union of normal cones to edges of the Newton polytope. But in that definition, all I care is the Newton polytope, right? So I might as well start with the Newton polytopes. Okay, so I can start with the Newton polytope and I get these tropical varieties. And then I can take this intersections. So I could, right? I could take what I said, stable intersection is one, I take these fans and then I translate them in the generic direction, right? I may or may not take the limit back, okay, or stable intersection. So the question is this stable intersection connected through codimension 1? Connected through codimension 1, meaning that if you remove all the codimension 2 or more things, it is still connected. Okay. Is it connected through codimension 1? Okay, so even if you did not digest this, I'll give you a translation to a commutative algebra problem. So using the fact that, right, tropical variety of irreducible ideals are connected, okay, this will be done if I know the following. So here is a commutative algebra problem. So you fix a Newton polytope, so you fix monomial support. Maybe I can fix monomial support. think of monomial supports of k polynomials in n variables when k is less than, strictly less than n, right? If k is equal to n, then I will expect that if I take k polynomials in k variables, then I'm going to have finitely many solutions, right? So the question is, I take f1 and fk with this monomial support with generic coefficients. Yeah. So the question is the ideal generated by them irreducible? Or is the variety of the ideal irreducible? Or maybe I could also ask, is the ideal or is the radical of the ideal prime? Yeah, does that make sense? Okay. This is a purely commutative algebra problem, right? So I fix a monomial support. If I pick generic coefficients, if you look at the ideal generated by those ideals, it's the radical prime, right? Okay. What do you think? Yes or no? Yes? Yeah. Okay, so there are kind of weird cases that I mentioned, like maybe near the beginning of the talk, similar to the weird cases, right? Maybe my ideal is like, although there are k polynomials in n variable, right? Maybe some of them live in a lower dimensional subring, right? A polynomial subring. So it's like, so maybe there's a subsystem that is like secretly zero dimensional, right? If it is zero dimensional, you don't expect it to be, right? Zero dimensional or like a bunch of a bunch of points, right? That is connected, right? So, you may have like this weird secretly zero dimensional stuff. But if you avoid that, and then you will expect that yes, right? If you take random polynomial, they should generate a prime ideal, right? So this is what I proved a while ago, actually. So maybe commutative algebra is known this long time, but I just couldn't find the literature. Okay, so my motivation is to do this polytope stuff, but then I reduce it to this commutative algebra problem. So this in 2016, I proved the following. So the answer is yes, if and only if you avoid this weird stuff. So is this prime? So the answer is it is prime, if and only if. So this is a condition on the monomial support, right? So it's some combinatorial condition of the monomial support. So for all non-empty subset of 1 through k, subset of the monomial supports. And then if I look at the dimension of the Minkowski sum of the Newton polytope of J, it is at least the size of J plus 1. That means that you're avoiding the secretly zero dimensional stuff, or the dimension is equal to the size of J and the mixed volume is 1. Okay, so if it is secretly zero dimensional, you better have only 1 point, right? It is still irreducible, okay? So it is obvious that these are necessary conditions, right? What is a little harder part is to prove that it's actually sufficient. Okay, so it's not too hard, it's just require the application of the right version of the Bertini theorem, right? So this is true. And what is even stronger is that in characteristic 0, you can remove the radical. In characteristic 0, you just get the straight up prime. What is not known, it is open to this day, in my knowledge, is that what happened in characteristic P. Okay, so in characteristic 0, so you can remove the radical sign. In characteristic P, of course, that you can have things where you have pure P powers, right? That's bad, okay? So, but how to phrase that combinatorially is not clear to me, right? So characteristic P, I would say that what is open is some kind of a combinatorial characterization, right? So you're gonna need this, but we need to add on extra combinatorial condition for this generic primeness. Yeah, is that clear? Okay. So I think this is a really sort of basic question that I will love to know the answer to. Yeah, although to get to my polytope problem though, characteristic 0 is enough. So I would not need characteristics for my polytope problem, but I think just, intrinsically, I think this is interesting. Although I should also note that, because the answer is yes, the answer to the thing upstairs, this question is also yes, under the same assumptions, right? Instead of monomial, you get the Newton polytopes, right? It's the same yes. And this is a statement purely about polytopes, but the only proof I know goes through all this. This is the only proof I know, right? So I do not know of a purely polytope way to prove this, right? So this is a nice example, in my opinion, of like, commutative algebra helping to prove some statement about polytopes, some connectivity of polytopes. Okay, maybe in the remaining 2 minutes, maybe I'll just talk through another project I was involved in. So that came out of WICA in 2019 in Banff. So my collaborator, Francesca Gandini, Melina Herron, Diane McLagan, Fatima Mohammadi, Jenna Redcott, Ashley Wheeler. So all these people were looking at what we call a toric Bertini or tropical Bertini problem. So Bertini says that if you have an irreducible variety and you slice it with a hyperplane, right, and then you get not something irreducible, right, if the dimension of the original thing is at least 2. So the question is it true tropically? If you have a tropical variety, right, so tropical variety. Okay, so in tropical variety, we don't have a good notion of what it means to be irreducible, but we can talk about tropicalization of irreducible variety. That's fine. If you have a tropicalization of an irreducible variety, you slice it with a usual hyperplane. Is this still, again, tropicalization of an irreducible variety? If you translate to commutative algebra, you're saying you have an irreducible ideal. You throw in a random binomial, right? Remember binomials? Tropicalized to usual hyperplane, right? So we throw in random binomial. Is it irreducible, right? Well, okay, what do we mean by random? For binomial, the coefficient doesn't really matter. What you care about is the exponents, right? So if you have a binomial, so if you look at the exponent, right, the difference of those two monomials, right? So you look at in the space of all direction vectors, right? Projective space of say q to the n, right? So the space of like the good ones, okay? Is it somehow like open and dense? So you can have a very simple examples where, yeah, you just write a quick example. Hold on, I lost my place in here. Let's say that if I have an variety of x minus x1 minus x2 square, x3 square. Okay, so this is irreducible variety, right? And then I'm going to slice with a binomial. So I throw in another binomial. Let's say x1 to the a1, x2 to the a2, x3 to the a3 equal to 1. You slice with this another binomial. So you get something irreducible. Well, you can see that, if these a's are even, no, if a1, a2 are even, it is not going to be irreducible. Okay. All right, because I can move a1, a2 to the other side, right? You get the square minus square, okay? So that means that the set of all the bad guys is dense. If you look at all the even vectors, right? In sort of, to the end, is dense. The set of bad guys is dense. But how about the set of good guys? Are they also dense? That is an open problem. Okay, so right here, yeah. So I will just write this. I then I'll end the talk. So with my WICA group, we have an answer. We don't have this in this generality of like you slicing things with binomial. We have some version of it, but it is a little rather technical and complicated. So I'm not going to write this. But what is still open is that you start with a variety is irreducible. And then you have you slice with a binomial. Yeah. So the question is the set of all the set of binomials, say x to the a minus 1 equal to 0, right? So the set of a such that the intersection is irreducible, right? The slice is irreducible. The set, is it dense? in some projective space of, Q. Okay, does it make sense? Yeah. Okay, so we have some progress toward this, but not in this full generality. And then this one, actually, but what we had is we got an answer to this question, but strong enough to imply the tropical Bertini theorem, which implies all kinds of nice things in tropical geometry. Yeah, so this is, I want to highlight the interplay between commutative algebra and tropical geometry, and here. Yeah, thanks.